Hello, my friends. It is Tuesday, June 2nd, and today we're going to start talking about our natural transmutation reactions. So yesterday I gave you a quick rundown in the live lesson about what a nuclear reaction is going to look like. We talked about how we need to see the isotope notation, and you're going to need to look at the mass and the atomic number when you're doing this. So today what we're going to do is start off with the first page of our kind of like a worksheet packet. So you're going to keep referring back to this packet throughout the week, and I'll tell you to keep going back to that June 2nd note packet. So this is something that you're going to be doing, and I can very easily check in and click on the note packet to see that you're up to date with all the work. And that way I'll be able to check any assignments that we have to do. So what we're going to do together today is this first page. All right, so we're going to work on this first page together and then move on from there. So just to get through the notes with this first page. Natural transmutation requires only one reactant. So if you remember yesterday, I said that it's always going to be one thing breaking down into two things. You got one reactant, two products, because it's that natural decay, and it's just going to release either that alpha, beta, or that positron particle, or gamma radiation. So it requires only one reactant because these represent isotopes which are naturally unstable. The only reason they're releasing something from the nucleus is because they're unstable. You can find a partial list of unstable isotopes in reference table N. And that's this one right here. Okay, this whole list here. So they tell you it's a partial list. Those are the only ones that you're going to be asked to work with. During nuclear rearrangement, radiation is emitted. The most common types are alpha, beta, or positron. Okay, for this reason, unstable isotopes are also called radioisotopes or radionuclides. Now, when we say the word nuclide, this refers to any particle of the nucleus. Okay, any particle of the nucleus. Now, up until this point, we've always said it's protons and neutrons in the nucleus, which is true. That hasn't changed. But what we discussed a little bit in Monday's lesson is that some of those particles can break down, and we can actually get smaller particles, something like a beta particle or a positron we can get out of there. All right, so any particle that comes from the nucleus is a nuclide. Now this graph here, this graph shows us this line of stability. Now, if you have a 1-to-1 proton to neutron ratio, that indicates you have a fairly stable nucleus. All right, so what do I mean by that? If I have carbon, and the most common isotope of carbon is carbon-12, that means I have 6 protons, 6 neutrons. That's a 1-to-1 ratio. If I have nitrogen, the most common isotope of nitrogen is 14. I have 7 protons and 7 neutrons. Calcium. All right, most common isotope of calcium is calcium-40. And the reason is because I have 20 protons and I have 20 neutrons. So when you have that 1-to-1 ratio of protons to neutrons, you have a fairly stable isotope. What happens though is that as atoms get larger, the neutrons kind of run away a little bit. And we don't have that 1-to-1. So you have more neutrons than you do protons. And if you start looking at some of the masses, you start to realize like, oh yeah, there's, those masses are much higher. They're not just double. So if I were to take a look at something like mercury, All right, we'll just try to use some easy numbers here. If I looked at mercury on the periodic table, the most common isotope of mercury is mercury 201. Now, mercury has 80 protons. But if I take a look at that, if I subtract 80 from 201, that's going to give me 121 neutrons. Okay? So 121 is definitely quite a bit more than, you know, the 80 if it was a 1-to-1 ratio. So that's when we're going to start seeing unstable isotopes. All right? So the graph above, we go to number 2, the paragraph there. The graph above shows points representing stable elements, and the line shows where the number of protons and the number of neutrons are equal. So for light elements, the ideal ratio is close to 1-to-1. For heavier elements, the ideal ratio of neutrons to protons, so again, neutrons to protons, is greater than. So we're starting to get more neutrons than we have protons. More neutrons are needed for heavier elements because it seems to stabilize the repulsion. We have to remember that protons are all positive and they push away from each other. So the neutrons start to stabilize that. And that's why you start having more and more neutrons, because you keep getting more and more protons. Those neutrons try to break up that repulsion within the nucleus. Transuranic elements, heavier than uranium, and uranium has an atomic number of 82. Nope, I'm sorry, uranium 92, off by 10. Okay, uranium, anything higher than 92, no stable element exists. So once you get to that point of 92 or higher, they are all unstable. And there's some that are even a little bit below 92 that are very unstable. So that number of protons and neutrons cannot be contained. Those elements are not stable. So now what we're going to do here is do exactly what we talked about in yesterday's live lesson about how to write a nuclear reaction. The first thing I need to do, and I'm going to put a little note here over on the side. First thing we're going to do is we're going to get the decay mode from table N. Okay, we're going to get the decay mode. The decay mode is what particle is emitted by that particular nuclide. So I take a look, I have, let's see, we have gold, 198, we have FR220, we have K37, we have RA226, let me make sure I can see all this. We have N16 and we have Ne19. So all of these radioactive isotopes are on table N. You need that to happen. All right, so the first thing I'm going to do is write down the particle. So Au198 releases a beta particle. So I'm going to put that beta particle. Now, if you remember, I need masses and charges. So beta, second one on the list, mass of 0, -1 charge. So I'm going to put a mass of 0 and a -1 charge. Francium 220, alpha decay. So I put the alpha symbol there. The alpha particle has a mass of 4 and a charge of 2. So 4 on the top, 2 on the bottom. Potassium 37, right here. Potassium 37, positron. So if you remember, if you flip over, the positron is kind of like a positive electron. Mass of 0, +1 charge. Ra226, alpha again. Okay, alpha again, and alpha has that mass of 4 and a charge of 2. Next we have nitrogen 16. Nitrogen 16 is going to go through beta decay. So I'll put the beta symbol, mass of 0, charge of -1. And finally, neon 19 is a positron. So mass of 0, +1 charge. Okay? So that's the first thing we do, is we figured out what particle is going to be released when this reaction goes through decay. So that's going to be one reactant. That's our first reactant. I'm just going to put a plus sign next to each one, so I know I have to figure out the other thing. The second thing you're going to do is look up the nuclear charges of the reactant. And that's the same thing as the atomic number. There we go. Okay, so you're going to look up the nuclear charges of each of those reactants. So you're just going to need your periodic table. All right, so AU 198, 79. I'm going to put that down on the reactant side. Francium 220. All right, francium FR 87. Potassium 19. RA right here, number 88. Nitrogen over here on the right side, number 7. And lastly, we have neon on the right side, number 10. Okay, so now I have all the information I need to figure out that last product. Okay, so now this is where we're going to go through and we're going to figure out that unknown second product. Okay, so we do that. We're going to balance mass. Sorry, that's my dog shaking her collar quite a bit in the background. So we're going to balance the mass and charge to find the second product. Okay, so we balance the mass and charge. So that means mass on the left equals the mass on the right. I'm going to move this over to the middle a little bit. All right, so if you remember, beta has a mass of 0. So if I start with a mass of 198 and I get rid of something that has no mass, the mass does not change. Okay, in fact, let's go through and do just the mass for all of these examples. And I said in the live lesson, like it would be like saying like how much a person weighs. If somebody weighs 198 pounds and gets rid of 0 weight, they still weigh 198. But if someone weighs 220 pounds and gets rid of a mass of 4, they now have a weight of 216. All right, 37 gets rid of 0. We are still at 37. 226 gets rid of 4. We're at 222. 16 gets rid of 0. We're still at 16. And 19 gets rid of 0, so we're still at 19. So now we got the masses, so we're all good. Now we have to figure out the atomic numbers or the nuclear charges because that's what's going to identify that last product there. So with beta, if you remember with a beta, it's a negative charge. So if I have a 79 as the nuclear charge and I got rid of a negative charge, that nucleus will get more positive. It will go up 1 unit to 80. Okay, so if you start with 79, get rid of a negative charge, what is the new charge? it got positive by 1 unit because we lost or released that negative charge. 87 gets rid of a charge of 2. We got 85. 19 gets rid of a charge of 1. We have 18. And if at any point this is going too fast for you, pause the video, go back and check your numbers and make sure you have everything the way that it should be. 88 gets rid of a charge of 2. We're at 86. 7 gets rid of a negative 1, so that means we go up to an 8. And 10 gets rid of a charge of positive 1, so we're down to 9. So right now I have my masses and my nuclear charges for all 6 examples. I use that bottom number to identify what the element is. Remember, the bottom number is the nuclear charge or the number of protons. So number 80 on the periodic table, if you take a second to look that up, is Hg. Okay, Hg. Now that is a completed nuclear decay reaction. For letter B, number 85 is At. Again, that is all balanced, so we're good to go. Letter C, 18 is argon, Ar. Now that one's all set. Letter D, 86 is Rn. Letter E, atomic number of 8, is oxygen. And for letter F, atomic number 9 is fluorine. So there we go. So the way you check your work is you add up all the masses on the left and you make sure they equal to all the masses on the right. So 198, 198. 220, 216 plus 4 equals 220. And you do that with the bottom numbers also. That's balancing for mass and charge. Okay? So that's our natural decay reactions. So what you're going to do is continue on onto the next page. Okay? And you're just going to complete the following. Okay, you're not going to do all of these. Let me just scroll out a little bit here. You're not going to do all of them because they're not all natural decay reactions. There's actually a couple that are artificial here. So right now, I'm going to circle the ones that you're going to do. So we're going to take a look at number 1, number 2, number 3, number 8. Okay? Now, if I asked you to figure out the rest of them just by going by the balancing, you absolutely could. Okay, but we're going to go into that on Thursday. We're going to talk about artificial transmutation and artificial reactions, and we'll also talk about fission and fusion, which are incorporated on this worksheet, so we'll talk about that later on. Okay, so you're just going to work on those 4 because those are natural decay reactions. All right, so that's it for today, guys. After we get through this and we do the rest of the work on Thursday, I will post the answers for you on Thursday, and I did mention that there will be no live lesson on Thursday, so I'll have another video posted that goes over artificial transmutation and also review the natural one a little bit as well. All right, have a great day, everybody. Message me if you got any questions.